You all for standing by, and welcome to our webinar entitled Impacts of Applying Drinking Water Residuals with Algal Toxins to Ohio Soils. This webinar series called Freshwater Science will highlight Ohio's Sea Grant and partnering scientists every month. Every quarter is a different focus, from human health and fish farming to harmful algal blooms and human decision making, bringing applied research to the public on issues that affect our Lake Erie communities. I am Jill Gentis Banicki from Ohio Sea Grant and Stone Laboratory, and joining me today is Nick Basta from The Ohio State University. Dr. Basta is a professor of soil and environmental chemistry within the School of Environment and Natural Resources at Ohio State. His research focuses on fundamental biogeochemical processes that affect heavy metal and trace element bioavailability, human health, and ecological risk in soil water systems, as well as development of innovative chemical methods and techniques to evaluate soil chemical processes and soil components that control bioavailability and risk of chemical species like nutrients and contaminants, and the creation and evaluation of new technologies used for remediation of contaminated soils. We're delighted to have Dr. Basta here today to talk about his ODHE funded Harmful Algal Bloom Research Initiative project. But before we do, just a few things about the webinar itself. During our presentation, all participants will be in a listen-only mode. Afterwards, around 12:20, I'll conduct a question and answer session. If you would like to ask a question during the presentation, please feel free to pull up that chat feature at the bottom of your screen anytime during Dr. Basta's talk, and I'll collect and pose your questions out to him at the end of his presentation. As a reminder, this webinar has auto captioning and is being recorded to be posted onto our website for later viewing. Also, we will post a webinar survey in the chat feature toward the end of the half an hour. Please take a few minutes after the webinar to fill out that survey. It always helps us to continue to bring you great webinars. So without any further delay, I'd like to introduce Dr. Nick Basta, presenting impacts of applying drinking water residuals with algal toxins in Ohio soils. Dr. Basta, you should be good to go.
Okay, you can hear me fine?
You sound great.
Okay, good. Well, first I'd like to thank Jill and the Freshwater Seminar Series for the opportunity to invite me to share some of our research findings from our ODHE project under HABRI. Today I'll be talking about toxic algal blooms and how they relate to beneficial reuse of drinking water treatment residuals when they're used as a liming soil amendment. Okay, and so I am sure there are many people on this webinar understand the issue, some better than I, with harmful algal blooms. Basically, toxic blooms, if it's blue-green algae toxic blooms, can release cyanotoxins, and a common cyanotoxin that's released is microcystin. And so microcystin can cause serious health effects. If there's a drinking water standard to prevent those health effects, they include severe water loss, liver function, etc. A little over 10 years ago, we had a crisis with a toxic bloom in the city of Toledo. The microcystin levels were high enough, they exceeded the US EPA drink MCL, the drinking water standard, for 2 days, which meant no drinking water. It was quite a crisis. People bringing in tankers of truck and everything else. So this is where this actually came to a head. Now, a different topic is the water treatment residuals. So I want to explain a little bit about what we're talking about, because there are different residuals. This water treatment residual is a byproduct of drinking water production. One type of residual that's generated is from water softening. If you have hard water, the treatment actually makes soft water and a byproduct. And that byproduct contains calcium carbonate. And it turns out that's a very good liming material, excellent liming material for agriculture. So these residuals are called lime WTR or lime sludge. And there are other types of waste generated at the water treatment plant, like elm sludge. I'm not talking about that today. I'm talking about drinking lime sludge or drinking water sludge. Now, sludge is a terrible word, isn't it? It's actually an engineering term that means more than 0.2% of solids. So you have 99.8% water and 0.2% solids. It's a sludge. So it's a technical term. These materials, so on the left, you can see the water plant, drinking water plant, and on the bottom, the waste product from that treatment is stored in a lagoon, and you can only see that this is the lime softening sludge. You can see the calcium carbonate, the white and the calcium carbonate. When these get filled, or close to being filled, they're commonly applied to farmland to adjust the soil pH for crop production. So they're used as an alternate liming material. And that benefits I mean, it's very expensive to landfill a lagoon. So if you have to do a clean out of a lagoon or dispose of WTR, it could be millions of dollars. So it provides economic benefits to the water treatment plant and society at large, since we're the ones who pay that water bill. But it also benefits agricultural producers because it's giving them an inexpensive source of liming material, which they need periodically to apply for crop production. Research about 10 years ago started, and some of it was published in 2017, about microcystin that can be absorbed, can be absorbed into vegetables or crops. So in 2017, Lee et al. Showed that fresh produce in their soils can accumulate cyanotoxins. The system was from irrigation water. So the cyanotoxins were in irrigation water. When it was applied to land, or in their case, they could actually see uptake. Uptake into lettuce, carrots, and green beans. So this had nothing to do with water treatment residuals, but just a proof of concept that you can absorb microcystins from water. I and Dr. Jiyoung Lee's group showed in 2020, published that drinking water residuals, they did a study to look at if the cyanotoxins you basically are concentrated in the lime sludge during water treatment, can you wind up having uptake from the water treatment residual into food crops? So they did a study, and they showed uptake of microcystin by carrots and lettuce. And that raised concern. So because we've been land applying lime sludge for many years, and we don't want to apply, we want to do no harm. So if there's microcystin in these materials, and the only place you really see microcystin appreciable amounts are areas that have had source water that have had harmful algal blooms, but they are out there. So the main concern is in this exposure pathway from microcystin. If it gets in WTR gets land applied, will it migrate to drinking water? So leaching of microcystin to groundwater. And the second concern is if it's absorbed in the crops, can you actually have degradation of crop quality? Now, previous studies I just mentioned, the irrigation studies, show that you actually can have uptake. There's a few hydroponic studies that show you could have uptake. And limited WTR greenhouse studies that are more proof of concept, because the amount of WTR that was used in those studies was 20 to 50% by weight. That means 20 to 50% of the growing media was water treatment residual. Proof of concept means you use a high concentration to see if you can actually get uptake. Typical agronomic rates that OEPA permits is less than 1% WTR in soil. So you can see in practice, farmers are not applying that much WTR to constitute 20% of green and growing medium. They're usually much less than 1% WTR. And so but the ones that had the 20 to 50% WTR in the study showed uptake of microcystin from carrots and lettuce. And so this project that was funded was effective soil properties on leaching potential. So we want to see if soils actually can retard the movement of microcystin to groundwater, and crop uptake. Do we see crop uptake of microcystin? The original PI was Dr. Elizabeth Dayton. She retired, and I became the PI on this project. And then Dave Tomaszewski did a lot of the field work, and Shane Whitaker in the lab, and Dr. Lee was a collaborator. So the objective specifically is to look and see what kind of, what's the leaching potential of this if this WTR gets land applied to soil, to the soil properties, can it retard the movement of the microcystin so it doesn't wind up in groundwater? The second part of the study was a field study with field crops to evaluate microcystin uptake under field conditions at agronomic rates. So in this case, we weren't doing proof of concept. We were doing something that would be actually typical of what a farmer would do and see if we saw uptake. And we're growing soybeans here because that's where most of our farmers are growing, agronomic crops. Okay. So a little bit of the study. We went out to a plant that had elevated microcystin in its water treatment residual. We collected 20 kilograms of the material, brought it back, dried it, homogenized it. We had two studies. The lab column study was to look at mobility of the microcystin in soil. That contained 388 microgram per kilogram, part per billion of microcystin. The second source of this material, it does vary. The residual was the same, but the microcystin content changes with time, depending on the season. The field crop study had 173 microgram per kilogram. We selected 7 Ohio agricultural soils, a range of properties that would be relevant to partitioning between the soil and the liquid fraction. That being a range of organic carbon content. So you can see the soils are arranged by organic carbon content. We had a control sand. This was a pure sand material. There's no carbon in 100% sand, which would be for us to compare the soil against. The sand is the worst case. It should have the least absorption potential. And we went all the way from 1% to 6% carbon, clay all the way from 12% to 43%. So it was a good range of properties. In the column study, we added WTR to the soil at a 10 ton per acre rate. And 10 ton per acre is the highest you would go. That's like the upper limit for alignment material. We simulated that by taking 300 grams of soil and mixing it with 3.18 grams of WTR. And then we packed it in columns. We ran, we used method 1314, which is a EPA method to measure transport. It's an upflow percolation column procedure where you collect 9 fractions based on liquid solid ratio. After we collected the fractions that came out of the column, we stored the sample and then quantified the microcystin. We did not quantify individual conjugators. I mean, there's 60 forms at least of microcystin. We measured total microcystin. So we used the MMPB method of Foss and Abel, which basically has an oxidation step followed by analysis. So we converted everything to we oxidized it and we get a measured total microcystin. So I can't tell you what form of microcystin. All I can tell you is the total microcystin. The actual chemical analysis, we did this work in our lab, the preparation, but the actual analysis was done at the campus Chemical Instrumentation Center, CCIC, which is operated by the Office of Research. The crop field study, we applied WTR at a more agronomic prescriptive rate of 6.9 ton per acre. That was applied as a liquid. Most of the time, these are applied as a liquid, not dried. So it was 95 liters at 6.3% solids, The solids had 173 microgram per kilogram of microcystin. We surface apply incorporated to 4 inches. These were small plots, 4 square meters each. After it was incorporated, they were planted to soybean. Soil and tissue were samples, soybean samples, were taken at 1, 2, 3 months after planting. Grain was collected after 3 months. And we also looked at soil at different depths, 4 different depths. Tissue, grain, and soil were all extracted using acetonitrile and sodium bicarbonate, and then prepared for oxidation by MMPB, followed by analysis, just like the water samples at CCIC. So the results. So here's the results from the column study. What I want to point out is there's our sand, and you can see that's the highest line. The most comes out of the sand because it has no absorption, essentially. So we're seeing 12 microgram per liter coming out in the first fraction, drops down pretty quickly in the second fraction. And by the third fraction, we're not detecting any more microcystin all the way out. The soils are this group behave differently than the sand. You'll see lower concentrations coming out of the soils, and the soils are slightly different from each other. They range from maybe 3 to 6 microgram per liter coming out. When we actually analyze what properties seem to be affecting microcystin transport, 2 things popped up. They're inverse. We had a microcystin transport is inversely correlated with clay content and organic carbon content. So the more organic carbon and clay you have, the less transport. And that's actually why it's probably different than the sand, because the sand doesn't have any clay and it doesn't have any organic carbon. We did a mass balance. This is how much microcystin went into the columns for each soil. And these now are arranged by the amount of mass leached from the column. And you'll see that we applied 1.23 microgram of microcystin to the columns. And in the sand, essentially, it all came out, 1.19. But in the soils, it didn't all come out. You see 0.54, which means a little less than 56% was still in the column. It was retained in the column. And it varies slightly, but it's generally 40 to 60%. Soil 2 was much lower at 26% retention. So you might ask, well, would we expect that? Well, we expected most of the microcystin to leach. There are different forms of microcystin. A common one is LR. And LR is typically has a negative charge at the pHs of typical soils, which is between 5 and 8. And it has a low log KOW value. So it really isn't very hydrophobic. So we didn't expect to see much retention. That's why the concern. These would be highly mobile in soil. Other forms have different charges, but generally they're mostly negative, but you do see things like RR can be positively charged. In that case, the cation exchange capacity could retain some in the soil. Okay, in the field study, we went out 3 time periods, collected samples, and took 4 soil samples with depth and analyzed microcystin. So we saw essentially about 1.89 to 2.3 part per billion microgram per kilogram in the top 5 centimeters. None of the other soil fractions had detectable levels of microcystin. And our detection limit was 0.14 microgram per kilogram, which is pretty low. So it's pretty much staying in the upper 5 centimeters. Plant tissue, we collected a lot of plant tissue samples and grain samples, and they were all BDL. We didn't see anything in the leaf material for the soybean, which means it was below 0.14 microgram per kilogram, and the grain did not have detectable levels of microcystin. So if you compare it with one other study, I et al. In 2020, that was a greenhouse study. We did a field study. We did soybeans, they did carrots. But the biggest issue, I think, is the I et al. Study, they were using a much higher rate of WTR, 20 to 50%, where in our experiment, we're using less than 1%. The soil microcystin, you get measurable amounts in both studies, but there's 5.4% of the microcystin applied wound up in the edible parts in the carrots, but nothing was detected in the soybean. So what we were seeing with beans, there's a lot of differences here. Field studies are different than greenhouse studies. In greenhouse studies, the pots are small and the roots actually exploit a lot of the pot. In a field study, the roots only occupy about 1% of the volume. So this is not uncommon that in a field study, you would see less uptake just because of the root soil contact. The roots occupy much higher than 1% by volume in a potting study in a greenhouse. So the conclusions that we can reach from our study, this was not a study to answer everything. It was a study to take a look. And our conclusions would be that microcystin leached as expected, but we were surprised that half of it was retained. And subsequent pumping of eluent through that did not desorb anymore. So it seemed to stay retained in the soil. When you land apply, the uptake of microcystin from agricultural land, when you're putting out agronomic rates, which are no more than 1%, showed non-detectable or insignificant levels of microcystin in soybean leaves and grain. Organic carbon and clay enhanced microcystin absorption. OEPA guidelines, the interim guidelines that were put in place, assumed conservative values of 100% leaching of the microcystin. So, our study shows that there's some degree of protection. We might have been getting 50% leaching, but we weren't getting 100%. And so in a way, the OEP guidelines that were put in place actually provide some protection from land-applied microcystin associated with lime sludge. And with that, I'll take questions.
All right, we have several questions. So let me just start with a couple of clarifying questions that a few people had asked, and these were questions posed out like in the earlier portion of your presentation. One question was, why do farmers have to raise pH in their soils?
Oh, okay. Well, generally, most farmers in Ohio are growing crops like corn and soybean, and are adding nitrogen fertilizer to grow those crops. The nitrogen fertilizer is usually ammonium, and the ammonium is converted, the ammonium actually is turned into nitrate and acid. So over a period of 20, 30 years, you actually get a buildup of acidity in the soil. And if the pH goes too low, below 5, you start losing crop yield. It starts damaging the crop. So you have to maintain the pH above 5, 5.5. So farmers monitor this with their soil testing program. And when the pH eventually gets below a certain point, 5.5 or 6, whatever they select, they realize that if they can't let the pH go down anymore from nitrogen fertilizer, so they have to lime. So the liming is a one-time deal that may last 20 or 30 years. I mean, I compare it to putting a roof on the house. You don't put a roof on every year, but when the roof starts leaking, you do put another roof on, right? So that's why they do it.
All right. Another question, just to clarify, you had mentioned several crops that you were using in your study, and then you had mentioned the adding in soybean.
Right.
Could you talk a little bit about which crops, just to clarify, which crops you were using in your study? And a couple of people asked if like corn and wheat were in this study. So I just want to get a little clarification of which crops we were talking about.
Soybean.
Okay.
We really focused on soybean, and we had good growth in the soybean and everything else. I mean, this could be, if we want to study more crops, we can. But this project was not really meant to cover all crops. We were more concerned about taking a quick look, since soybean is the dominant crop in the state, followed by corn. We wanted to take a quick look at soybean to see if we were seeing uptake into the soybeans at agronomic rates under field conditions.
All right. Another question that we had was considering that WTR are lagooned and microcystin benefits from UV radiation, should WTR be heat treated prior to lagooning or at least isolated from UV radiation?
Well, if somebody wants to remove the microcystin from the WTR, that's great. If people are willing to use those techniques, heat treatment or something, that's fine. But most of the time, like I was mentioning, they want a liquid apply because it gets incorporated well into the soil. So, heat treatment is going to require you drying the material down, and the application will be a little different.
Okay. Another question is, do microcystins under these conditions in the soil affect the growth of some plants?
Well, that comes down to concentration, really. And there are studies out there that show, like under the irrigated ones, where you have high concentration of microcystin in the water, that it can affect plant growth. But, it all comes down to how available the microcystin is it in the water, and the concentration. And I think that's the thing we have to pay attention to is if you read a study, and they did a hydroponic study, and they said the plant growth was stunted, you have to ask how many part per billion of microcystin was in the water, and was it continually replenished? See, with this thing, you put out WTR, the microcystin isn't continually replenished. It's applied once and that's it. So in some of these studies, they'll continually supply contaminated water. So you have a fresh supply of microcystin all the time. You got to read the study and look at the details, but you can design a study to show phytotoxicity of some plants. And that's fine. We call them proof of concept studies. We want to know if it's possible. So we'll go to high concentrations to see it. Then that's how we saw uptake into some vegetables, and we also saw there could be some phytotoxicity. But then the next step is, okay, so we know it can happen. The question is, when it's done in practice on farmland, does it happen? And that's where it's no longer a proof of concept, where you got to use realistic concentrations and one-time applications. You can't just keep feeding water with contaminated water.
Okay. Another question we have was, how much absorption is the upper limit for soil integrity?
Oh, it's pretty high. These are tiny amounts. So we're not even close to any the absorption capacity is not the limiting factor. The question is, does the microsystem, what's its affinity to be absorbed to organic matter or clay? But we're not even close to, if that's what you're wondering, we're not even close to absorption. These are tiny, tiny amounts that are being absorbed.
What's the typical percentage of lime available in WTP, WTR?
Well, that depends on the source, but I've seen some that are pretty good ag limes. They're pretty high percentages. So ECCE's effective lime calcium carbonate contents approaching 70–80%. So they could be very effective ag lime materials.
All right.
But they do vary, and people will have to test them. So they get tested to see what lime value are. When you're actually figuring out how much to put out as a liming material, you get your soil tested for pH and lime requirement. And if the pH is too low, you get a prescription of how many tons of effective calcium carbonate you add. Then you have to test the WTR, and then you apply it based on the recommendation.
All right. Let's see. And sorry, I'm getting more and more questions. So
A lot in the chat. That's good. We
yes,
got
and
time.
okay, so another question we had from this study, would you feel agricultural application of lime sludge is still an effective reuse option for these residuals?
Yes. Yes. I mean, you know, I will say that if we don't have detectable amounts of anything in the crop, I don't see any harm there. I mean, we do see tiny amounts that move and leach, but we didn't really see much in the subsoils. So I would expect to see something in the subsoil. So I would say yes.
Okay.
Now, somebody might say, well, what happens if um, but the data I've gotten of field conditions, it looks like it's a good practice and a safe practice.
All right. Another question we had, the concentration of MC is likely to vary throughout the year
Yeah.
with bloom activity. Do we have a sense how the concentrations detected in WTR vary over time?
Yeah, they do vary. Late summer, they go up. When the blooms get more intense because the source water has more in it. So that was the 388. That was coming from a collection period where there was more activity and the other material was a little lower. So it gives you an idea. I want to emphasize that this was actually one of the highest microsystems we've ever seen. So we used the worst case material. Most drinking water plants don't even have hardly any, well, probably not even measurable microcystin concentrations. So this is something that isn't everywhere, but you do have to pay attention. If your source waters had harmful algal blooms, then you should be testing for microcystin in your lime sludge, and it will vary. You will see higher concentrations in the summer, late summer than you will earlier. And the state requires now, OEPA requires you test for microcystin. And there are limits at how much microcystin is allowed. I think I'm trying to remember, the interim standard was in the 180 some part per billion, I believe. And so that would mean one of those materials, 388, could not be land applied, but the other one might just barely be land applicable. But this was the worst case that we tested, the highest microcystin we found in residuals in the state.
Okay. Did you find any examples of Hab toxin migrating into drinking water wells? Maine is
Yeah.
limiting WTR applications because of PFAS. Are we looking at a similar limit from Hab concentrations?
We wish we had that data, but this was a limited study. It was just looking at the migration through the soil and the crop uptake. So we did not have lysimeters or monitoring wells. Um, the PFAS question always comes up. We're still collecting data on PFAS. We're actively looking at PFAS in natural soils. We're finding PFAS in a lot of places. And so WTR, it seems to me, does not seem to be a good source of PFAS because it really doesn't have most of the PFAS inputs. You're just taking source water. It's not like biosolids where you would expect domestic and industrial inputs. In fact, what they're finding in biosolids is biosolids PFASs are not high unless you have significant industrial input, which they do have. But we're still waiting. We don't know what high or low means. So this month, we're waiting for US EPA to give us interim standards for PFAS well, not interim, guidance for PFAS and biosolids. So in January, I'll be able to tell you what's high and what's low.
Here's another clarifying question. what is the limiting factor? The usage amounts by farms or the amount of sludge produced?
Well, that's a good question. I mean, the limiting factor is how far they can transport the material to a farm, because transportation costs money. So generally, if there's a farm that's 50 miles away that needs lime material, they're not going to probably transport something 50 miles. Um, so I think the big factor is that, most of this material, a lot of it is land applied, but not all. And the reason it's not all is it could be the transportation costs. It could be other factors that it just isn't economical to transport that far.
Okay.
Did I answer your question? I mean,
I-
in some plants, they have a surplus. In other plants, they have no surplus, depending on their location. So you really want to have a place that's close to agricultural land.
Okay. Um, Another question that we had was, from this study, would you feel agricultural application of lime sludge is still an effective reuse option for these residuals?
Yes. Yeah,
Okay.
I think we're all, we're reassured now. Uh, More reassured, I should say. Now, are we perfectly reassured? I'm a researcher. I'm never perfectly reassured. But I don't see, I think it was reassuring for us to conduct this and see that we're okay with this as being a beneficial use.
All right. Um, I have two more questions. I'm sorry, I'm just making sure that um I have, okay. So one question was, could you talk a little bit about the impact of drainage tiles on leaching? Tiles which is prevalent in Ohio farms on transport from soil to waterway.
Right. Well, uh, tile drain systems are made to drain fields to remove excess water. So they do accelerate transport. That's their purpose. And so, is that what they're asking?
Yeah, I think so. And I'm sorry, it's a two-parter.
Okay.
Um, and let me just, sorry, I scroll a little bit and then it gets away from me. In the field study, oh shoot, sorry, it keeps on moving. In the field study, oh shoot, sorry, I might not be able to give you that clarifying, that additional question. It keeps on rolling on me here. Okay, there's one kind of last question that I had several people ask.
Okay.
Um, One is, what do you feel is the next step in this research?
Uh, I will write a report. We'll send it to OEPA and they will actually review it and see if they want to make any changes to their guidelines or not. Um, Now, further research, we always would like to see another research study. So we can do something more extensive if it was necessary. We might do one on corn and wheat, like someone had mentioned, or you could put lysimeters. There's a lot of things we can do to extend this, but I think right now, what we have is kind of reassuring, I should say.
All
We
right.
went into this thinking for sure we were going to see uptake because we were thinking, well, we saw it in carrot and lettuce. We're probably going to see some uptake. But then we thought, well, the big greenhouse studies got their, like I had mentioned, have got their caveats. I've done a lot of greenhouse studies with metal work, and I can tell you the metal uptake is greatly enhanced compared to the field, and that's well known. So you really got to go outside and take a look in the field. And we looked in the field, we didn't see the uptake.
All right. Well, looking at the time, I actually think we should probably end since we're now 20 minutes into this Q&A session. So this was really great. So let me just kind of wrap up here and Dr. Basta, are you okay if people have additional questions just to reach out to you?
Absolutely.
All right.
And
Perfect.
I'm okay with you sharing the presentation and, yep,
All
absolutely.
right. Great. I will add your email address to the email I send out to folks with the recording. And anyone who is interested in Dr. Basta's PowerPoint presentation, can just email me and I will get that to you. I wanted to again thank Dr. Basta for his willingness to talk with us today about his research. This was really an excellent discussion. So thank you, Dr. Basta. I also wanted to remind everyone that our survey URL for this webinar is in the chat feature, so please take a few minutes to fill that out. This webinar series is sponsored by Ohio Sea Grant and will continue in January with Ohio State's Dr. Shedekar, who will be discussing his research on a new tool to help drain design for on-site wastewater and stormwater treatment systems. The registration link is in the chat. Again, thank you, Dr. Basta, and thanks to all participants on this webinar. We hope that this was beneficial and hope that you'll join us again in an upcoming webinar. Thanks again and have a great afternoon. Thanks again, Dr. Basta. This was great.
Thank you for the opportunity.
Absolutely.
Okay,
Have a great rest of the afternoon, and I'll send you a few things soon.
please. Okay.
All right. Thank you, everyone.